Integration by parts is what we're doing now. And we're going to learn a lot of integration techniques. We've already learned a couple of integration techniques. If you think about substitution and all those rules that we learned earlier in calculus. And coming up after integration by parts later on will be trig substitution and partial fractions. There's a lot of different techniques, but out of all the techniques, I think U substitution is the most important, and integration by parts is probably the second most important integration technique to remember for courses later on. And in a nutshell, we can think of integration by parts as integrating or undoing the product rule. So let's take a look at how we would get into that. Let's think about differentiating using the product rule. So I'm going to differentiate the function here. So p of x is a function f times g. Now if I were to differentiate that, so p prime would be equal to, okay, differentiate the first function, leave the second function alone, plus leave the first function alone, the derivative of the second. So that's just me differentiating using the product rule. And now what I'd like to do then is solve for fg prime. So solve for this piece here. So f g prime is equal to, well, that's equal to p prime minus f prime g. Okay, so far so good. Now it says here just integrate both sides. Okay, so I've got this equation and I'm going to integrate both sides. So I'm going to integrate fg prime with respect to x, and I'm going to integrate the other side, the right hand side, with respect to x. Oh, and if I integrate something minus something else, that means I can just integrate that side or that piece, integrate. So I'm just integrating each piece separately. Oh, and integrate p prime with respect to x. This whole side here, if I integrate p prime with respect to x, that's just p. And what is p? P is f times g. Here's my this is my integration by parts formula. So this is important. Let's put it in a box. If you've seen this in other places, integration by parts in other places, sometimes people write it with U's and V's. F's and G's and U's and V's. It doesn't matter. It's the same formula. If I'm integrating two things multiplied together, one of them is a function and the other one is the derivative of a function, we can swap out our integral. So let's take a look at let's take a look at an example, and I got a couple of examples down here, but let's pick an easy example to start with. So I want to match the idea here, but before we even do this example, let's start with an even easier example. So I'm trying to integrate x times e to the x. Now, first off, I'm matching the pieces here. I'm matching f is x and g prime is e to the x. I guess I could match them the other way around too, but just to start, let's match those pieces. So I'm making f equal to x, and I'm making the g prime equal to e to the x. That means that, so I've got f and g prime. That means f prime would be equal to 1. I'm differentiating with respect to x. And g would be equal to e to the x. I'm integrating with respect to x. So now I've got the four pieces, f and f prime, g prime and g. So let's plug this in the other side of our integration by parts. F times g, these diagonal, that's f times g minus the integral of the two things I made. That's the way I remember it. So it's the two undifferentiated pieces minus the integral of the two things I made. I made the one, that's the f prime, and I made the e to the x, that's the g, dx. So notice that this technique doesn't actually finish the integration. It basically changes one integration problem for another integration problem, which is okay as long as the other integration problem is easier than the one that I started out with. So I guess the question is it? So can I integrate, I'll get rid of that one, can I integrate e to the x? Yes, integrating e to the x is just e to the x. And now I'm done, so tack on a plus c. So it swapped, our original problem was swapped out with a different problem. That different problem was easier, or at least not any harder, so we solved it, and now I've got my answer. I've integrated x e to the x. If I differentiate this, and I'm going to expect you to check that, if I differentiate the answer, I should get back the question, x e to the x. Let's try this with another example. So I'm matching the idea with, so let's take I've got f g prime. So I need to decide here, I'm integrating x times ln x. I need to decide which piece am I going to integrate and which piece am I going to differentiate. So I'm going to differentiate the x, and I'm going to integrate the ln x. So f prime is going to be, I'm differentiating the x with respect to x, that's just 1, and now I need to integrate ln x. I don't know how to do that. So switch them then. Instead of, because I can differentiate ln, so instead of differentiating the x, I'm going to differentiate the ln x. So I'm switching parts. If I differentiate the ln x, it's 1 over x. And if I integrate the x, yeah, I can do that. That's going to be x squared over 2. So I chose for the part I'm going to differentiate the ln because I could differentiate it. So now let's put this in. We're matching these pieces here. It's f times g. It's the two undifferentiated pieces. So there's one undifferentiated piece. There's the other undifferentiated piece. I wrote it as g times f just because it makes it look better, but that's f times g minus the integral of the two things I made. So here's the two things I made. The f prime and the g dx. Now, can I integrate this? That's the question. This technique is working if my resulting integral is easier. And it is, right? Because I can cancel this x on the bottom with this x squared on the top. I can write this as just x over 2 if I cancel it, and now I can integrate that. So let's do our integration then. If I'm integrating x over 2, that's going to be an add 1 to the exponent, divide by what's up top, so this becomes a 4 on the bottom, and that's our integral, plus c, integration by parts. So in this example, our first example, everything lined up nicely. In this one, we learned that the piece if I have a piece that I can't integrate, then that should be the piece I differentiate. Let's do some more examples. The rest of this integration by parts is mostly done with practice, so we can encounter all the little pitfalls that would happen. So I'm keeping you can read through these notes here. Let's do another example. I've got x cos x. Now, there's the two parts there. I can differentiate x, that becomes 1, or I can integrate x squared over 2. I can differentiate cos, minus sine, or I can integrate cos, sine. So both pieces I am able to differentiate or integrate. So how would I make my choice? Well, I'm going to choose to differentiate the x because it gets simpler, goes to 1. If I integrate it, it becomes x squared over 2. And I'm going to integrate the cosine. Now I got to be careful. Differentiate sine, I get cos. Yes, careful to keep the right sign. But that's going to give for me an easier integral. So let's put those pieces in then. That's going to be f times g minus the integral of the two things I made. So I made 1 and I made sine x. So I'm going in the right direction if this new integral is easier than my old integral. And I guess it is, right? The old integral was x times trig. The second integral, the new integral, is just trig. So let's integrate that. If I want to integrate sine, that's going to be minus cosine plus c. And I guess I can clean this minus a minus up to be a plus. So my final answer would be x sine x plus cos x plus c. Verbally, and that way if I remember it verbally, then I don't have to remember it with the u's and the v's or the f's and the g's. It's f times g, those are the two things that are not differentiated, minus the integral of the two things I made. More examples. Okay. I need to pick a piece to differentiate, and I need to pick a piece to integrate. So, if I differentiate x cubed, it's going to become 3x squared, so it's going to get simpler. My instinct is that's the way I should go. That means the piece I'm going to integrate is going to be the sine of x cubed, the piece that I'm going to integrate. All right, so let's differentiate the 3x, or the x cubed, that's 3x squared, and let's integrate the sine x squared. Okay, I don't know how to integrate, so let me just write down what my problem is that I can't do right now. That's my problem. I would like to do u substitution where I let u equal to x squared, but I'm missing an x on the front here. Let me just watch this. We don't have to write this down, but what I would like to do to solve this integral is let u equal to x squared, and of course then I say to myself, substitution is at least a two-part process, so du dx would be equal to 2x, and then I would solve this du dx for, I'd solve it for dx is equal to du divided by 2x, and when I put those pieces in, then I would get the integral of, in place of dx, I'd write du over 2x, and this would be u. But my problem is that this x didn't cancel on the bottom. I wish there would have been an x here on the outside. I wish there would have been an x in front of the sign so that this x would have canceled. That's what I wish. Oh, wait. I had 3 of them, but I put them all in the f side. I think what I should have done is let's make this squared and leave this as an x. So I'm repicking my f and my g prime. I'm leaving one of the x's in the g prime. So now I'm making f equal to x squared. So my f prime is now just 2x. It still gets simpler. And when I'm integrating then, when I'm integrating my g prime, because there's an x there, when I do all this substitution, the same substitutions, there's an x here now. And this x cancels with this x, and now I'm integrating 1/2 sine u, so g becomes minus 1/2 cosine u. Okay, now I push this all down here because this is something for, like, I'll have you check this over. When we're doing integration by parts, it looks like I had this piece here, x sine x squared, and I integrated it kind of in my head, although this is all the stuff that happens in your head. But I've got the g. Let's check this out. If I differentiate, oh, not with the u here, this x squared. If I differentiate this, derivative of cos becomes minus sine, so minus sine, and that's going to cancel. Chain rule says 2x is going to come out, the 2 is going to cancel with a half, and yeah, okay, we're good. So that all of this substitution is just a small little part of our parts. Okay, so integration by parts. F times g f times g. Let's make this a minus x squared minus the integral of the two things I made. Okay, the two things I made are this f prime and this g. When I multiply them together, that 2 is going to cancel this 2. This minus sign is going to come outside to make this a plus. So this is the minus the integral of the two things I made. It was supposed to be a minus here, but this minus sign canceled out that minus sign to make it a plus. Now, we're going in the right direction if the new integral I made is easier than the old integral. Oh yeah, this was x cubed times trig, and now this is x times trig. It got easier. All we have to do is this last integral. So let's clean this up. This, oh, we already integrated x times trig. We can do this integral. That's going to be sine x squared. Now let's check. If I differentiate this, that's going to become cos x squared times 2x. I only have the 1x there, so I'm going to balance it with a half. Or I could do u substitution again. Now I'm almost done. Tack on a plus c, and now I think I am done. Integration by parts, integrating this x cubed sine x squared. The purpose of this example, or what I would wanted to show you, is that the splitting the integral up into two parts is not always obvious. Trig wasn't, this trig sine x squared wasn't the part, it was x times this. We needed to match this derivative so that we could do u substitution. Let's do one more example. Integrating ln x. Oh, up here, way up here, the second example that we did, we made the f the ln because we couldn't integrate it, so we could differentiate it. And now in this example I'm asking you to integrate it, but where are the two parts? I can differentiate ln, but I can't integrate it, and here I'm asking you just to integrate it. So I want you to think that there's a 1 in front of there. That way, I'm going to do the same idea. I'm going to make the function, and I'm going to make the f ln, because I can differentiate ln, and I'm going to make the g prime the 1, because I can integrate it. So when I do differentiate the ln piece, I get 1 over x. And when I integrate the 1, I get x. Okay, so I could do each piece. So parts, f times g, so x times ln x, minus the integral of the two things I made. The two things I made are 1 over x and x. When I multiply them together, it's just 1 dx. And can I integrate 1? Yeah, I can. It's just x. So the answer is going to be x ln x minus x plus c. Now I've got a rule for the integral of ln. Now I can differentiate ln, 1 over x. I can integrate ln, x ln x minus x. Now I've got a new rule. The algebra trick here, or the calculus trick here, was if I only see one part and the thing I'm trying to integrate is something I can differentiate but not something that I can integrate, then make that the part you differentiate and make 1 the other part. I said that was going to be the last example for this video so that we can do all these other examples. We can do all these other examples later in the next video. But I lied. Let's do one more example, sort of to hammer home on this point here. So I'm going to integrate, and I want to choose something like ln, something that we can integrate, or something, sorry, that we can differentiate, but we can't integrate. So I know how to differentiate arctan, but I don't know how to integrate it. But I'm going to do the same idea here. I'm going to make 1 times arctan so that I have one piece that I can differentiate, the arctan, and the g prime, I'm going to make that the 1, just like we did here. So I can differentiate, f prime is equal to, I can differentiate the arctan, 1 over 1 plus x squared. And I can integrate the 1. So now let's do integration by parts on this. It's going to be f times g. The f times g, it doesn't make any difference what that is because I don't have to integrate it. It's just whatever it happens to be, minus the integral of the two things I made. The two things I made are 1 over 1 plus x squared multiplied by x. So the process is going well if this new integral is easier than this original integral. Oh, and I can do this original integral. If I let u equal to, I'm going to do u substitution. If I let u equal 1 plus x squared, it's going to work out to be ln. So I got x arctan x minus the ln of 1 plus x squared. This x on the top is the result. When I differentiate ln, I get 1 over 1 plus x squared times 2x. Oh, times 2x. So I need this, I need a half in front for balance. Now, you could get this, you could solve this integral by doing a u substitution. I'm sort of guessing and checking, but you could do it with a u substitution as well. Why don't I have the absolute value bars around here? Because 1 plus x squared is always positive, so I don't need the absolute value bars in the ln. These two examples, what they should show you is if I'm trying to integrate something that I can differentiate but I can't integrate, put a 1 in front, use that as one of the parts. And then that swaps out my old integral for a new integral that I can do. My old integral for a new integral that I can do.